Hey everybody, it's Mr. Dan. In this video, I'm going to talk to you some more about gas laws, a bit of review, and then something new for you. Okay, so review is the gas laws that we've already covered in class, starting with these three, Boyle's Law, Charles, and Gay-Lussac's. So Boyle's Law, relating pressure and volume to one another in an inverse relationship, meaning that as one goes up, the other is going to go down. This situation only works where temperature is held constant as well as the amount of gas. We've also got Charles' law here. In Charles' law, we're relating volume and temperature. This is a direct relationship, meaning they both go up together or they both go down together. Okay? This only works when pressure and the amount of gas are held at a constant, or meaning they don't change. Gay-Lussac's, relating pressure and temperature in a direct relationship, again, both up or both down together. Constants are volume and the amount of gas. And the final one is the combined gas law, where pressure, temperature, and volume all work together. Constants are the amount of gas. Okay? Here we can see all three of these equations working together. Look, it's combined gas law. Here's Boyle's right there. You want to see Charles' law, that's volume and temperature. And then if you want to see Gay-Lussac's, that's pressure and temperature. Oh, I got a little messy right there. That's okay. You can see, though, that they're all present there in the combined gas law. Okay, so we already know about those. Remember the examples that we worked on in class just the other day. Okay, next slide. New thing, we're going to talk about Avogadro's principle. That's right, the same Avogadro. Sometimes this is called Avogadro's law. If you don't remember, Avogadro is the guy who gave us Avogadro's number, which means that 1 mole of a substance has 6.02 times 10 to the 23rd particles of some kind. It's just a counting number. So that same guy gave us some gas laws too. Avogadro's law states that an equal volume of all gases at the same temperature and pressure contain the same number of molecules or moles. Okay, so take a look at the example of the balloons here. Notice how all the balloons are the same size, okay? What this is saying here is that for each of these, look, there's 1 mole of 3 different gases. Okay, so we know from our stoichiometry that 1 mole of helium has a mass of 4 grams. I'm looking at the periodic table right now. 1 mole of oxygen, I guess it's right here as well, has 32 grams. Okay, and 1 mole of nitrogen has 28 grams. But despite that difference in mass, the volumes will remain the same when we're talking about gases, okay? This is because those teeny tiny gas particles are spread super far apart, okay? A little bit more on that in a moment. Avogadro went a little further, and he said that for 1 mole of any gas at STP, the volume will be 22.4 liters. What's STP? STP is standard temperature and pressure, meaning temperature at 273 Kelvin, always Kelvin, which is a temperature of 0 degrees Celsius. And the atmosphere is 1 atmosphere, or 101.3 kilopascals. These two are equal to each other. Okay? So when we say STP, or standard temperature and pressure, we mean these two right here. Okay. So 1 mole of any gas at standard temperature and pressure will equal 22.4 liters. Because of that equal sign right there, we can turn these into conversion factors, and we're going to use that a little bit later when we talk about gas stoichiometry. That's right, there's a section in this chapter called gas stoichiometry. I know you're super excited. Okay, so the main thing to remember here, though, is that equal quantities or moles will have equal volumes as long as they're held at the same temperature and pressure. Okay. Next. the ideal gas law. Okay? This is the one law to rule them all. The equation for it is PV equals nRT, where P is for pressure. You can use atmospheres, kilopascals, there's millimeters of mercury, there's other things. I just listed two. P is for pressure, V is for volume, and liters, milliliters are fine too. N is for moles, T is for temperature, no Celsius. R is for the ideal gas constant. The ideal gas constant is derived from our equation. Oops, let's see here. With PV equaling nRT, if we combine all these and solve for R, we'll get pressure times volume divided by moles times temperature. And if we look here, we have pressure, or volume times pressure divided by moles times temperature. I think that's what I said. Okay. These numbers have units. We need to use this number whenever we're using the ideal gas law. And we have to pick the correct one of these. Usually it's going to be either this one or this one, as atmospheres and kilopascals are the most common. But we have to put one of these two numbers into our equation every time. Okay? So, going back to the ideal gas law then, the way this works is we're going to be given a set of information, and you just have to plug the numbers in and solve for the one thing you don't know. So it works out pretty nicely. Here are the numbers again for the ideal gas constant. Okay. So what is an ideal gas, you might be asking yourself? Ideal gases state that particles have zero volume, there's no intermolecular forces between them, there's constant random motion, they move in straight lines until a collision, and the collisions are 100% elastic, or there's no energy transfer going on. Basically, we're describing the rules of the kinetic molecular theory here. Okay? In reality, there are no true ideal gases. There's always a little something that's wrong with this, but nonetheless, we have the ideal gas law, and we can apply it to most situations. Some gases can deviate from ideal when they meet a certain set of conditions. Those conditions being that maybe they are held at a very high pressure or a very low temperature. Some gases are polar, like water vapor would be a polar molecule, and also very large non-polar molecules. The larger they are, the more mass and volume they have, and the more they start to break these rules up here. Remember, large molecules, even if they're nonpolar, have a greater attraction for each other than small ones due to their London dispersion forces. Okay, so how can we use this law then? Let's look at an example. The idea here is that we can solve for some unknown aspect of the variables, pressure, volume, temperature, moles, maybe density, maybe grams. We can solve for that if we're given a certain set of criteria. So when we're given a problem, we just have to figure out what information do we have, what information do we need to find out. Okay, remember those questions from the other day. Where am I? Where am I going? How will I get there? What will I need to get there? Okay. Let's read the example. 2.5 moles of carbon dioxide are stored in a 3.0 liter container at 15 atmospheres. What is the temperature of the gas? First thing I want you to do here is figure out, where are you? What information are you already given? Well, we're given moles, 2.5, volume, and pressure. Where are we going? It says that we want to know what is the temperature of the gas. So that's our unknown there. So that's where we are and where we're going. How do we get there? Well, given this information, I've only got one number for moles, one number for volume, one number for pressure. Given that, I know that I'm not going to use Boyle's law or Gay-Lussac's or combined gas law or Charles, because those all require two volumes or two pressures or two temperatures. In this instance, we only have one of each. So that's going to lead me to the ideal gas law. So right? What we're doing is we're answering how are we going to get there. Given that I'm using the ideal gas law, I also need to figure out what the ideal gas constant is. So I'm going to look to my pressure here because that unit is going to tell me which number for the ideal gas constant I want. My pressure is in atmospheres, so the ideal gas constant that I'm going to use is 0.0821. All right. So now I know where I am, I know where I'm going, and I know what I will need. Let's go there now. Let's find out what the temperature is. So I'm going to plug these numbers into my equation. Pressure, 15 atmospheres. Volume, 3.0 liters. Moles, 2.5 moles. R, 0.821. And I went ahead and put all the units in here for us. And then T for temperature. That's what we're solving for. I left it in red so we could track it. Okay. So here's how the ideal gas constant works. It works so that we can cancel out all these other units and be left with just the one that we need. Okay, so before we do anything with the numbers, here's what happens when we work just the units. Okay? If you work this out on your own longhand, I can't show you very well on this. We can see that atmospheres will cancel, liters will cancel, moles will cancel, and all we're going to be left with is Kelvin for our temperature. Okay, so that's exactly what we want. Next, let's start combining those like terms or combining those numbers. So 15 times 3 divided by 2.5 divided by 0.0821. Run that on your calculator, and you're going to get 45 over here, and then 0. Blah, blah, blah. Okay? You don't need to write out all those decimals on your paper. You'll just have that running on your calculator. Okay, so we're just solving for T here. It's pretty simple. We're going to get 219.4 Kelvin equals temperature. Okay? So this is really just kind of a plug and chug thing. Once you figure out what you have and where you're going to go and how you get there, you just start plugging numbers in, and you should be able to pretty easily churn out an answer here. So I'm going to assign some practice problems for you guys, and you're going to work on them and send me any questions or thoughts you have about them if you have any problems working those out. So good luck. I hope this is helpful. See you guys later.